Imagine a bat, a whale, and a human waving hello. What do they all have in common? No, it's not that they all have bones. Well, actually, it is about bones. If we look closely, their limbs all share the same fundamental structures. But wait, what about a bird and a butterfly? They both fly for sure, but their wings couldn't be any more different. This brings us to two major concepts today in comparative anatomy: homologous structures and analogous structures. Think of evolution like a big family tree. Sometimes relatives grow up and take on different jobs. One cousin becomes an artist, another a scientist, and another a chef. But they all share the same grandparents. That's kind of how homologous structures work. These are body parts that come from a common ancestor but have changed over time to serve different purposes. Here, take a look at the limbs of mammals, birds, reptiles, and even amphibians. If we strip them down to the bones, you'll notice something similar for all of them: one upper bone, two lower bones, wrist bones, and fingers. This blueprint is called the pentadactyl limb, and it is a classic example of a homologous structure. In humans, it is used for grasping and tool use. In bats, it is stretched into wings for flying. And in whales, it is modified into flippers for swimming. Same structure, but different function. That's divergent evolution in action. Now let's talk about analogous structures. These are body parts that look and function similarly, but evolve independently. Now imagine two people showing up to a party in the same outfit, but they never met and they didn't plan it. That's what happens in convergent evolution. Different species face similar challenges, and over time, these species develop similar solutions, adaptations, and evolutions per se. For example, we have the wings of birds and insects. A bird's wing has bones, muscles, and feathers, but an insect's wing is thin, membranous, and made of chitin. Both help their owners fly, but their evolutionary origins are completely different. Another example is a shark's fin and a dolphin's flipper, which look almost identical. But sharks are fish, and dolphins are mammals. Sharks evolved streamlined bodies through fish evolution, while dolphins evolved them much later on as mammals adapted to water. This is the power of natural selection. Even totally unrelated animals can end up looking alike when they live in similar environments. But why do we study this? Comparing homologous and analogous structures helps scientists piece together the evolutionary puzzle of life. Homologous structures tell us about their shared ancestry, while analogous structures show us how nature solves similar problems in different ways. So the next time you see a bat flying, a whale swimming, or a butterfly flapping, remember, their bodies are all carrying their own evolutionary stories. And that's comparative anatomy. So if you've liked this short video, give it a thumbs up and subscribe, or support us through Patreon for exclusive updates and content. And as always, thank you for supporting this channel, and everyone, stay curious.